Conversion dropped 12% after deploying PPR. Users saw a flash of $29.99 before the price updated to $34.99. The problem? The price was rendered outside any suspense boundary, so PPR baked it into the static shell at build time. The experimental PPR. Incremental config shown in the article requires Next.js 16. In earlier versions, 14.15, PPR was enabled with experimental PPR true and applied to all routes automatically. The incremental mode was introduced in Next.js 16 to allow per route opt-in via export const experimental PPR equals true. If you are on Next.js 15, use PPR true instead. The article mentions that PPR is global, but you can opt out a specific route by setting export const experimental PPR equals false in the page file. This forces full dynamic rendering for that route while keeping PPR enabled globally. PPR streams dynamic content via Suspense, but if a dynamic slot takes too long, e.g., 10 seconds, the connection may time out or the user may see a blank fallback indefinitely. Set a reasonable timeout on your data fetches inside Suspense Boundaries and consider using abort controller to cancel stale requests. Monitor streaming duration in production to catch slow slots. The article discusses performance benchmarks, but doesn't show how to measure streaming duration in production. Use the Performance Observer API to track when dynamic slots resolve and log the time between static shell delivery and dynamic content arrival. Let's break down partial prerendering in Next.js 16, the complete guide, how it works, and the exact mistake behind that failure. Partial prerendering is a rendering strategy that mixes static generation and server-side streaming in a single page. The static shell, navigation, layout, product images is pre-rendered at build time and served from the edge. Dynamic parts stream in via Suspense Boundaries. At build time, Next.js pre-renders everything outside Suspense Boundaries into a static shell. At request time, the shell is served instantly, and dynamic content streams into the suspense slots. The browser progressively renders the page. Here's the typical structure. Static components like header and gallery are outside Suspense. Dynamic components like price, reviews, and cart each have their own suspense boundary with a skeleton fallback. This is the product page with PPR enabled. Notice the experimental PPR export and the suspense boundaries around dynamic components. The static parts are outside Suspense, the dynamic parts are inside. The product price component fetches real-time data, user session, product from database, and Stripe pricing. It applies user-specific discounts. This must run at request time, so it's inside a suspense boundary. This component fetches the user session, product data, Stripe price, and user discount. It returns the final price with a member discount badge if applicable. PPR is enabled globally in Next. Config TS. With incremental, you opt in per route. Dynamic APIs like cookies or headers. Outside Suspense force full dynamic rendering. Generate static params tells Next.js which dynamic routes to pre-render. Here's the config. Set PPR. Incremental to opt-in per route. Also shown is generate static params for a blog route. It tells Next.js which slugs to pre-render. Suspense boundaries are the control mechanism. Components outside are static, pre-rendered at build time. Components inside are dynamic, streamed at request time. Granular boundaries let each section load independently. The bad pattern wraps everything in one suspense. The whole page is dynamic. The good pattern uses granular boundaries. Each card, table, and chart streams independently. Fast sections appear first. Benchmarks show PPR delivers TTFB 94% faster than full dynamic rendering, 18 ms versus 320 ms. FCP is 84% faster. Server compute costs drop 62% because static shells are served from Content Delivery Network cache. This table compares rendering strategies. PPR's TTFB is nearly as fast as full static, while LCP and TTI are close to dynamic. The streaming timeline shows progressive rendering. 3 common patterns. product pages with static catalog data and dynamic pricing, dashboards with static layout and dynamic metrics, content pages with static article and dynamic comments. Choose based on how often data changes. Here are the 3 patterns. Each has a different suspense boundary strategy. The product page has the most static content, so it benefits most from PPR. PPR and caching are complementary. The static shell is cached at the content delivery network with ISR. Dynamic slots can have short TTLs. React Cache deduplicates fetches within a request. Use revalidate tag for on-demand invalidation. The static shell uses ISR with hourly revalidation. Dynamic slots use 60-second revalidation. React Cache deduplicates the product fetch. On-demand revalidation with revalidate tag instantly busts the cache when data changes. Cache components generate HTML once per TTL. They must be deterministic, no user-specific logic. If your cache component calls getServerSession, you're defeating PPR. Move session checks into dynamic boundaries. The correct cache component uses a URL-based cache key and no user data. The broken version uses userid, which creates unique HTML per user and destroys caching. This is the same issue we highlighted at the start. Here's exactly why conversion dropped 12%. The price component was outside any suspense boundary, so PPR pre-rendered it at build time with the price $29.99. The dynamic slot only contained the cart item count. Users saw the stale price instantly, then the correct $34.99 after 200 ms, and lost trust. The price component was placed outside any suspense boundary, causing it to be pre-rendered at build time and served stale. Moving it inside a suspense boundary with a skeleton loader fixed the issue. The fix was to move the price component inside a suspense boundary with a skeleton loader. Now the static shell has no price, it streams dynamically. We also added on-demand revalidation via revalidate tag, so the shell is invalidated when prices change. Conversion recovered to baseline. This is the mistake that caused the 12% conversion drop. The product price component is outside any suspense boundary, so PPR pre-renders it at build time. The price becomes stale as soon as data changes. Wrapping the entire page in one suspense boundary defeats PPR. The whole page becomes dynamic, no static shell is served. TTFB is the same as full SSR. Calling getServerSession in a cache component generates unique HTML per user. The content delivery network cannot cache it, so every request hits the server. MoveAuth checks into dynamic suspense boundaries. To debug PPR issues, first check that dynamic components are inside suspense boundaries. Measure streaming latency by tracking time to first chunk versus full response. Compare TTFB before and after PPR. Use Lighthouse CI to catch regressions. Let's run through some common interview questions. What is PPR and how does it differ from SSR? PPR combines static generation and streaming. SSR renders everything per request. How do suspense boundaries affect PPR? They define the split between static and dynamic content. Outside is static, inside is dynamic. What caused the 12% conversion drop? Price component outside suspense was pre-rendered with stale data. Users saw incorrect pricing. And a few frequently asked questions. Can I use PPR with ISR? Yes, they complement each other. Static shell uses ISR dynamic slot stream. Does PPR increase bundle size? Negligibly, adds KB for suspense streaming infrastructure. When should I avoid PPR? When dynamic content is critical to initial render, e.g., checkout totals, login state. Let's recap the key takeaways. PPR mixes static and dynamic in one route. Suspense boundaries control the split. Cache components must be user agnostic. Measure TTFB, FCP, and conversion impact. Ready to go deeper? Up next, building type-safe forms with Zod, React Hook Form, and Next.js 16, then 10 common Next.js 16 app router mistakes, and how to fix them, then Supabase auth with Next.js 16 and TRPC v11 plus Next.js 16, complete setup and best practices. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at thecodeforge.io.